Hello, today we are going to be learning about implicit derivatives, definite integrals, and antiderivatives or indefinite integrals. So let's start with what an implicit derivative is. So if we look here, we have not a function, definitely. We have you could say a graph or a circle, and I've drawn a tangent line here to symbolize I want to find the slope of this tangent line. And our change is going to be constant, actually. Right? So if we move a dx, dy can be anywhere. This is not a function, right? But since it equals a constant, it does have to be going up, going this way, and going back. It has to stay on the curve, or in this case, on the line. So right now what we're trying to do is figure out the behavior of these slopes. So this is a dy by dx triangle, and like I showed you, dx and dy are almost the same thing. Almost, but of course not quite. But as you can see, dx is here, and I said for some functions that have multiple inputs, like this, right? It's weird, but yes, those kind of functions exist. For those kind of functions, what we do is, and since it's equal to a constant, actually, like I said earlier, we move like this, and then we move like that. We keep it on the curve, but sometimes you don't have to. You can move off the curve. But the change in this function, so let's say this is s of x comma y equals 1 squared. And the change in this, the derivative, not really with respect to anything, but this change is, I'm just using d for change. The change in 1 square is 0. So ds, or delta s, whichever you like, honestly, is equal to 0. So that means this value s isn't changing, and therefore we move back on the curve, right? But for implicit derivatives, I don't think of these two as inputs, but rather as separate functions. Whatever keeps them separate, because dx and dy are very clearly not related, because I can move this and I can go here or here, but only because this ds is constant, I can't. So first, you could take the derivative not with respect to anything. You could do this. Notice how it's not with respect to anything. It's like with respect to question mark. Right? With respect to question mark. So what's that? Well, you could think of both of them as sharing a common input. So x of I, right? For lack of a better variable, I use I. X of I plus y of I, obviously squared, equals 1 squared. And this is simply the change in this function the total change of this, again, it's not a function. The total change here is equal to a constant, because the derivative of a constant with respect to anything is 0. So this thing is not really changing a whole lot. The net change, I guess, is not, there's kind of no change, right? This, if you call this a multivariable function, the net change is 0. So if you think of these as their own inputs, or if you put in I explicitly, what you would get is 2xi, because it was x of I, the whole squared, times dx over di, plus 2y of I times dy over di equals 0. So all of this equals 0. But here, this I stuff isn't even there. That's implicit. The input is implicit, so you get that. And now, if you divide everything by x, you get 2x plus 2y times dy over dx equals 0. And now, with some further algebraic manipulation, you get the derivative of y with respect to x of this circle is negative x over y. Now, I really want you to think about it as their own functions, except this I is implicit. I didn't do that on purpose, but you could say I is implicit or input. Implicit. That I is implicit, so x and y aren't really tied together, but you assume they are, sort of. Right? It's a little complicated. I hope I haven't confused you, but the best way to think about it, and I guess I'm being redundant, that x and y are functions of their own, but their input is implicit. And actually, we can use this technique to get new derivatives. And one thing I also want to point out was when we took this implicit derivative, x of y, I'll just put this for a shorthand. Actually, no, I don't want to. X of y squared plus y of I squared. When we did this, right, this was the implicit derivative, but eventually we divided everything by x, right? So in a way, we sort of did do the whole derivative, just in a different way. So in reality, we've been doing the top portion of that derivative. We've been doing implicit derivatives without even noticing it. But this is actually how you would do most implicit derivatives. So let's say you have a function, the arc cosine of x, or cosine inverse of x, equals y, a function, which is this, right? So you don't know the derivative of this function, but you want to figure it out. So what you can do is, first, you want to take the inverse of everything, because what you plan to do is, since you know the derivative of cosine, you can try take the derivative of cosine, and then find a trick by relating something in there to x, because what you get is x equals cosine of y, right? Does that make sense? Because arc cosine of x and the cosine of that equals cosine of y. Well, this is just x because cosine of the angle this is basically the definition of arc cosine. What is the angle that when you input it into cosine, you get, what is the angle that you input to cosine to get x, which is your input to arc cosine? Missed the C over there. But yeah, that's how it works. Right? You get what I'm saying? So now that we have this, I'll just write it over here. But let's take the derivative of this, and we get d cosine of y equals dx, right? That makes total sense. And now, instead of just moving this over and doing the whole derivative, let's do the implicit derivative stuff. Because what we get will actually be slightly more useful. So let's treat y as its own function. So cosine of y of I. And now let's do the implicit input thing with the chain rule. So the derivative of this with respect to yi, right? Because we want to do it with respect to I eventually, times the derivative of y of I with respect to I. We don't know what this is yet, but we do know that this is negative sine of y of I times dy of I. I've lost space over here. Let me try again. Dy of I over di, except there is no di, so wherever I is, we just kick it out. And so we get negative sine of y times dy equals dx. And then, with a bit of algebraic manipulation, you move this over here as 1 over dy, and then do the reciprocal of everything. You get this, right? And obviously, sine of y definitely is related to cosine of y. And cosine of y equals x. And ultimately, you want to relate everything to x, right? Because you don't like getting derivatives in terms of the original function. No, that just seems weird, doesn't it? Right? Sine of arc cosine, what? No. So what we do here is we can write sine in terms of cosine, and by using trig identities, you can get sine of y equals the square root of 1 minus cosine of y, the whole squared, and we're taking the principal root this time. So sine squared of y plus, and this is just old notation, kind of gotten used to it, cosine squared y equals 1 by the Pythagorean theorem in the unit circle, right? So if this is 1, then this must be cosine of y, assuming this angle is y. And that's terrible handwriting. This is sine of y, right? And by the Pythagorean theorem, we get this, right? Whoops. So, again, with a bit of algebraic manipulation, which you can pause to check out, you get this, and probably noticed that cosine of y equals x. We were planning this, so sine of y equals 1 minus x squared. And the reason we don't do it in terms of negative sine of y is because, well, when you have a fraction with a negative term, with a term in the numerator or the denominator that's negative, at least, so if you had something like a over negative n, that negative would sort of go to the fraction and quote-unquote not belong to the n anymore. So that's why we're doing that. And we get the derivative of arc cosine of x with respect to x equals negative 1 over the principal root of 1 minus x squared. And now that we've learned about derivatives, and implicit derivatives, obviously, but now that we've learned about derivatives, we can get started on integrals. Boom. So what is an integral? Again, the best way to do it is with a graph. All of these things are good with graphs, aren't they? What an integral is the area under a certain portion of this graph, and all of these derivatives and integrals are approximations, because as h goes to 0, not when h equals 0. So these are approximations. So this is a good approximation, really good approximation. And the way you would write this is, and let's just set it in stone, is this. The derivative of, the integral of f of x over the interval a to b is whatever. It's b. No, it's not b, it's c. It's c. So this equals c, which is some constant. Because we're actually having a range, and integrals don't spit out functions. And actually, since the derivative is a function, you could write a derivative of a certain part of the function. So f prime of 1 is actually going to equal something. So the best way to see why integrals and derivatives are super related is by using velocity. So let's say that this is your velocity curve, and for some reason you don't know how far you've traveled, but you know all your velocities over this interval of time that you've driven your car, let's say. So what you want to do is find your total s, or distance that you've traveled. You probably know, or you might not know, that the derivative of s of t, where s of t is a function for distance over time, with respect to time, is velocity, which is a vector, but let's try not to get into that right now. So this is true. So since we have velocity and not this stuff, since we have velocity and not this function, we should try to reverse engineer this by moving this over here, right? To get ds of t equals, and I'm just going to write v of t as f of x. Actually, yeah, let's do that. A of x, where a stands for antiderivative. The derivative of a of, the implicit derivative of a of x equals f of x times dx. So what this does is it sums up a whole lot of implicit derivatives over a certain range. Now, isn't that cool? So you can think of implicit derivatives as portions of area under its derivatives graph. Like, whoa, that's deep. Like, whoa, whoa. So, what we want to do to solve for a of x is take the antiderivative, or indefinite integral, of all of this stuff. Right? And, of course, b over a and b a, blah, blah, blah. Right? But we're doing the indefinite integral right now. And to figure out the antiderivative, we need quite a few techniques. So this is going to take a lot of techniques. So we just saw that if we have capital F of x, which in the place of a of x, if this is true, then portions of area like this, portions of area under a derivatives graph are not integrals, but are implicit derivatives. So the implicit derivative of a function is portions of area under its derivatives graph, its whole derivatives graph. So they're teeny weeny portions or rectangles or whatever. And the reason we use f of x times dx, you can think of dx being this, the base of a rectangle, and then you have something that's rectangle-ish, and that's what matters. It's rectangle-ish. And then this is the height, f of x, right? Because these are all f of x. And then, as dx approaches 0, you get f of x times d of x times dx, right? And those are going to be like teeny weeny rectangles, right? Because I said they're rectangle-ish, but only because dx is pretty big the way I'm drawing it. So in reality, it's not going to be that big. So for solving integrals, we've got a couple of steps. First is figure out the antiderivative, right? And what integrals do is, since they sum up a whole lot of implicit derivatives, actually, I didn't show it then, but I'll show it here. Let me use a more contrasting color, red. So if you have something like this, so when you figure out the antiderivative, you figure out a new function. So instead of summing a whole lot of areas, each of these areas corresponds to a value on this. So this corresponds to this, and this corresponds to this. This teeny sliver of area, or teeny portion. This teeny portion corresponds to this point. Because in antiderivative, it's not always a line, and usually it's not a line, but here, the antiderivative acts as a way to model the behavior of these areas, which is kind of cool. But when we want to know sort of all the values between, we want to know the change between these values, or deltas. So we use f of b, since if we have b and a, this sliver corresponds to a, and this sliver corresponds to b. Actually, I should say f of a, f of b, whoops, right, minus f of a, and this is lowercase f of, let's say, box. I don't know, for lack of a better thing, box. This is lowercase f, and this is capital F. Right? So that leads us to our next ones, our next steps. Evaluate the antiderivative at the upper bound, which is f prime of b, and then evaluate the antiderivative at the lower bound and subtract this from the number we got at step 2. And these are actually numbers, right? So a definite integral gives out a number, and an indefinite integral gives out a function in the same way that a whole derivative gives out a function. But then when you evaluate the derivative at points, you get an actual value, like a function should. So let's just try to calculate some antiderivatives. And hopefully you get the hang of it. There's not much to be done here. So if the derivative of f of x equals 2x, f of x equals x squared plus c. Now why it's plus c, or c is a constant, because by the addition rule, when you add something, it's f prime of x plus g prime of x for the derivative of f of x plus g of x, right? So a constant doesn't change, so its derivative is 0. So that's like saying if you have the same line on with different y-intercepts, they'll still have the same slopes, right? The slopes are completely independent of those y-intercepts. So that's why you add a c, but then in the integral you get rid of the c, because you do, in this case, b squared plus c minus a squared plus c, and the c's just cancel out. You can sometimes tell what the c is by knowing what this f of a equals. Sometimes. Or knowing what it is at that lower bound, right? So if this is our initial velocity, then we know that, or if this is our initial position, which it probably is 0, then f of a equals 0. If you know what that is, you can probably have a good guess at what the constant is. And you can rewrite it as the indefinite integral of 2x times dx equals f of x. So the derivative of f of x with respect to x equals cosine of x. F of x equals negative sine of x plus c of x. Duh. For the same reasons that this equals this. Or we could write it as this. So basically, indefinite integrals are the inverse of implicit derivatives. And that's all for today. So we learned a bit about implicit derivatives, definite integrals, and antiderivatives, or indefinite integrals. So, until next time, I guess.